Hello everybody, Mr. Hinnon here, and here is a little bit of notes on the friction force. That's the next thing we're doing in chapter 4. It's going to be kind of the last major thing, but we'll kind of look at a variety of different kinds of problems because friction on a flat surface, friction on an incline, or objects on an incline, that'll be the next thing that we'll kind of get into as we finish out chapter 4. So the first thing when you talk about friction is this happens when you have any two surfaces that are rubbing against each other, that are in contact. And when you do that, so let's say I'm taking my fingers and I'm sliding them relative to each other. So I'm just passing them back and forth like this. There is a force that's parallel to this surface that's opposing the motion or the attempted motion of those two surfaces. And this is called the frictional force. I love this slide because what it gets at, let me grab that pin, is if you could look at this little surface closer, this little microscopic idea, basically what's happening is each surface is bumpy. And so as they pass over each other, it'll catch on those little bumps. And that's really what causes friction. As you have those things catching in those bumps, that's what's going to cause it. Now, the first thing that we have is you have the situation of the attempt at motion. So I love this picture here, and we talk about what we call static friction. This is the force that is opposing the attempt at motion. So if I apply a force here on this box and it's not moving, then the friction force, F with a little s there, so we're going to use a lowercase f to represent friction force, is going to equal that. These are going to be equal and opposite. So this F is going to equal this F. Then as I pull a little bit harder, so if you notice this force now gets larger, what's going to happen is this is going to get larger. So F is equal to friction. But they both got a little bit larger. Then when you just start something moving, so if you are sliding something and it just starts to move, let's say, let's see if you can see this. Let's say that I have my calculator here and I start to pull, and then boom, it starts to move. That first motion is you overcoming what we call static friction. And that static friction is going to have a maximum when you just begin to move it. So that's one of the key ideas. I apologize for my dog in the background. So to calculate this, we know that the static friction is going to be less than or equal to the maximum static friction. So static friction is kind of weird. It builds up to a maximum. Really what's happening is those pieces are caught. You're pulling. They're applying that Newton's third law, that equal and opposite force, until boom, you pop them out. So the equation for finding that maximum static friction force is this funny looking thing. This mu, it's a Greek letter mu, is the coefficient, let me move myself out of the way here, is the coefficient of static friction. So it's a number that indicates how rough or how smooth a surface is. And then we already know what this is. This is that thing called the normal force. So the normal force, that perpendicular force, affects friction force, which is parallel, which I would always think is kind of neat. Little side note, static friction actually does not depend on the contact area. So as long as it's the same type of surface, doesn't matter how much of it is in contact. The other one, since static is talking about impending motion, so the attempt at motion, when you're actually in motion, so if two things are moving relative to each other, we have what we call kinetic friction. But the equation looks exactly the same. So kinetic friction is the coefficient of kinetic friction times the normal force. So this is the coefficient of kinetic friction. The biggest idea is the values for the coefficient of static friction and the values of the coefficient of kinetic friction are not the same. Typically what always happens is you're going to find that static friction is larger than kinetic friction. So this is larger than that as you go down. Now, occasionally they might be equal to each other. If you notice this Teflon on Teflon, Teflon is in the no-stick pans that you put that makes it so nothing sticks to it, that everything slides really well, that they have the same value. And wood on wood, they're almost the same value. But typically, kinetic is smaller than static friction. So let's try a little example here. Let's say, move me out of the way here. Let's say that you have a sled and it's sliding along and it comes to a halt. This is going to happen because of kinetic friction. So if I draw a free body diagram of this sled, these are the three forces acting on it. We have a normal force acting upward. We have the weight or the force of gravity acting downward. So sometimes we call this Fg as well. And then we have the kinetic friction force that's opposing it. Notice that even though they're sliding forward, there's no force pushing them forward. That's just Newton's first law, that they want to stay in motion, but something is going to bring them from 4 down to 0. It's going to bring them to a stop. So how do I calculate this coefficient of, or this friction force, this kinetic friction force? The first thing I have to realize is this thing is not moving up or down, then it must be in equilibrium in that case, and the normal force and the gravity force are the same value. So I take mass times gravity to find the weight, and that's going to equal my normal force. So when I'm finding that friction force, which I'm just going to label with an F with a K so I know that it's kinetic friction, I need the coefficient of kinetic friction, so they gave that to me, 0.05, and then I'm going to need the normal force. But in this case, what I just pointed out is the normal force equals mass times gravity. Put in my mu k here, and so you end up with this little cute equation. I sometimes mix it around. I sometimes put the m in front, and I've referred to this as the mug equation. If I kind of ignore the subscripts. Some people flip these back and forth, and I've had some students that refer to this as the gum equation, which I actually think is better because it tells me that gum is sticky, and so it would cause friction on things. It doesn't actually matter, but this only works if the normal force and the weight are the only vertical forces acting on it. So if I wanted to find the kinetic friction force, what I would have to do for this particular problem is take 9.8 times the 0.05 times my 40 kilograms. That's the mass of this object. Calculate that out. Let's see, 9.8 times 0.05 times 40, and I get 19.6. So this girl sliding along on this sled has 19.6 newtons of force bringing her to a stop. Ta-da! Friction. So let's try another one. This one I think is kind of neat. This looks almost the same, but I've changed one little thing. Now I want to figure out how far does it travel. I want to find x here. This is going to borrow some equations from chapter 2. The first thing I would do is I could do exactly what I just did. Let's figure out what that friction force is. Fk is equal to G mu k times m. We actually already calculated that, so Fk is 19.6 newtons. Now what's happening is that Fk is causing a deceleration of her. So it's actually causing the acceleration, but if we treat to the right as positive, then anything to the left would be negative. Now, we don't actually write friction forces as negative because we just want the magnitudes, but the direction could be important. So the next step is this. I'm going to actually change my color here so you can kind of see my switch. So the next step is this friction force is going to become the F, or the net force in the horizontal direction, in my F equals ma. So we're going to figure out the acceleration of this girl in the horizontal direction. So what I'm basically going to do is I'm going to put in this 19.6, set it equal to the 40 kilograms times A, solve for A. So I've got 19.6 divided by 40, and I get 0.49. So this is her acceleration. Now, technically, this is negative because it's in the opposite direction. So when I actually put this in, this Fk, I should actually be putting in negative 19.6 to deal with acceleration so I can see that. The reason why is because notice I've put a positive x and this would be the negative x. So I've indicated a direction. So that's where the negative is coming in. But that's not my final answer. My final answer is to find x. So I have to pull out one of those equations from chapter 2. So the equation from chapter 2 I'm going to borrow, since I don't have any times, is Vf squared equals VI squared plus 2AX. If I solve this for X, I get that it's VF squared minus VI squared over 2A. My VF is 0. That's the final velocity, so I'll cross that out. So I have a negative, so I'm going to be taking minus, and then I'm going to take the VI 4, and that's going to be squared. So the negative is out front, and then on the bottom I have 2 times my acceleration, which is negative 0.49. So this negative and that negative are going to cancel each other and make it positive, which is good. I'm moving in the positive direction. And so I have to take 16 over 2 times 4.49 is 0.98. Divide this out, 16 over 0.98. And she moves a little over 16 meters, 16.3 meters. Great little problem. Now, there is an extra thing of this that I think is kind of neat. So notice that this is my equation for the friction force, and this is what I'm substituting it in. I'm just making it negative. So I'm going to do one extra little change here. Let's change into red. Nope, let's change into green. So if I set these two equal to each other, I want you to see something kind of neat that happens. I'm going to slide me over just a little bit because I'm going to put it right up here. So the force, it went back. I didn't want to do that. Let's go back. The force in F equals ma equals minus the friction. So if I put mass times acceleration equals, in this case, minus the GUM equation, notice something interesting about this. You may have even realized it already. The mass is on this side, the mass is on that side. I can actually cancel those masses. In other words, any person, it doesn't actually matter what the mass of this person is on this sled, as long as it's the same coefficient of friction, they would come to the same stop. Because I've developed kind of a new equation for finding the acceleration of you slowing down on this particular surface. So just a little neat thing with friction. We're going to do some more with friction this coming week and finish things out in chapter 4. Hope you enjoyed. I've thrown a couple of questions on the Google form. Get those knocked out as well. Take care.